Welcome everyone. So this week it's a great pleasure to have Frank Coronado from McGill University, and he will tell us about 10-dimensional symmetry in n=4 superiomials. Please, Frank.
Yeah, thanks a lot for the invitation to present my work. So I'll be telling you about some 10-dimensional symmetry we have observed at the level of 4-point functions at weak coupling. And this is work in collaboration with Simon. So yeah, I'll be telling you about 4-point functions of these single trace protected operators. As you know, they are extensively studied, not only because of their wealth of OPE data that can be extracted from it, but also the kinematical limits that can be studied. And another interesting feature is that they are subject to various to dualities and hidden symmetries that are not obvious from the Lagrangian description. So in particular, for the case of the smallest operator, known as 20 prime for k = 2, for scaling dimension 2, there is this duality, or actually it's a triality relating the correlator with some loop and scattering amplitude. And more recently, a couple of years ago, Simon and Ankoy observed some 10D symmetry, but in a specific regime, in the regime of strong coupling, when the theory is dual to 3-level supergravity in ADS. Basically, the way, just briefly, the way it goes is that they recognize that they can build a generating function for all the 4-point functions of arbitrary scaling dimension, first starting with just the simplest correlator of 20 primes, and extending, so taking the 4D distance enhanced to be a 10D distance that includes now the R-charge scalar product. So in an expansion for a small value of this R-charge scalar product, then you can get all the series of correlators. In this talk, I will be focusing on the opposite regime. I will be working on a weak coupling, and I'll be asking if there is also possible to observe some 10D symmetry. This will not be at the level of the correlator as it happened for the Sura limit, but now we will have to look at the INTEGRAND level. So there we were able to recognize some hidden 10D symmetry. So just let me give you an outline. So I will start with a review of what's known about these integrands for the integrand of 20 prime and also higher weights. And then, well, based on this wealth of data, I will show you that it's possible to repackage all of those results in a single generating function that has some manifest 10D symmetry. And
could I ask, so does it relate to the fact that n=4 is n=1 in 10D reduced?
Maybe. I don't have an explanation for the symmetry. So what I will be presenting is basically as an observation, but yeah, we don't have yet an explanation for it. Neither there is an explanation for the symmetry for the Sugra limit. So I think those are open questions. Maybe yes, it is, well, one has to go as what you suggest, like, but we haven't taken that step. And I will not be commenting on the origin of this 10D symmetry. Yeah, so, well, instead of that, I will try to take advantage of it by showing you some application. So I will consider this generating function for correlators, but then I will focus on a class of correlators that is about the correlators of operators with very large R-charge. And the way I will obtain them is by taking some 10D null limit of my generating function. And that will also allow me to show that these correlators of very large R-charge are also related to 4-particle amplitudes. So not only the original 4-point function of 20 prime, but also another class of correlators, but now with very large R-charge. And also in the same direction, this will allow me to to extend the map that Basso and Dixon started with fishnets and determinants of ladder integrals. So I will show you an example of how that can be extended. Yeah. So yeah, let me start with what's this 4-point integrand. I'm considering these protected operators, just traces of k powers of a scalar. And well, they are of course parameterized by the space-time position and also by some 6-dimensional vector that gives you the R charge polarization. And for protected operators, this is a null 6-dimensional vector. I'll be considering just weak coupling expansion. So I have this series, and the way I will obtain the integrand is by the Lagrangian insertion method. So this method allows you to relate the correlator to an integral over to an integral of a Born level correlator, where you have the original 4 external operators, but also n insertions of Lagrangian in order to obtain the n loop contribution. This Born level correlator, well, it's can be shown to factorize thanks to some probability. So it factorizes with this prefactor that I spell here at the bottom, and times something I call the reduced correlator.
Sorry, could I ask a naive question? So when you insert Lagrangian, do you also insert kinetic term? Because normally, like in canonical perturbation theory, you would only insert interaction part, right?
Yeah, this will be just the interacting part.
Ah, okay.
Yes, and so in principle, you can compute this correlator using Feynman diagrams, and I think that's the way it was originally done for 1 and 2 loops. But then it becomes increasingly harder. Instead, it's possible to perform a bootstrap of this reduced correlator, especially for the case of the smallest operator for 20 prime. Because then, as I showed you, this reduced correlator has very nice properties that allows to have a successful bootstrap program. So let me tell you about that simplest integrand. So one of its key features is that it's a rational function, and it only contains simple poles on these distances xij squared, and this can be shown from an OPE analysis of the Born level correlator. There is also a permutation invariance, not only of the external points, but actually the full set of points, the external and all the internal Lagrangian insertions. Well, this is maybe a bit harder to show, but basically it's inherited from the supercorrelator of the stress tensor multiplet, which contains actually both the 20 prime scalar operator as the bottom component and the Lagrangian as the top component. Conformal symmetry also imposes some constraints on this rational function. And in the planar limit, we also have the, as I mentioned before, the correlator amplitude duality, which at the integrand level can be spelled in this way, which you take some null square limits. So these are the distances between consecutive points. They go to 0, so they become null separated. And the result is the integrand of the amplitude square. But of course, the amplitude depends on momentum variables, and the way you map these two is by making this replacement where these distances map to the momentum of the external particles. And because I'm just working at the integrand level, here, this is just a relation between two rational functions. So there is nothing divergent as it happens when you integrate the amplitude. So these properties are very constraining, and as I said, then a bootstrap program can be performed. So these are some of the results up to 3 loops. The way the integrand is presented here is some bunch of poles, all the poles for every pair of points, the whole set of points, external and internal, and a numerator where the degree of the numerator depends on the loop order and is homogeneous. That's something imposed by conformal symmetry. And of course, you have this permutation invariance for all of them. There is some nice way of representing these integrands, which is some graphical way where each edge on these graphs corresponds to a propagator. And one of the conditions for that imposes planarity is that these graphs here, they should be planar in order to contribute to this planar integrand. Up to 3 loops, there is a single graph for each integrand, but this starts getting more complicated as you go to higher loops. So at 4 loops, you already have 3 of these graphs, and then you have to figure out what are the coefficients that weight each of the graphs. It keeps growing. So when you have 7 loops, for instance, you have 220 of these graphs, and so it looks much harder to fix the coefficients, but fortunately, people show that it's possible to study the divergences of this correlator in OPE limits and then translate those conditions at the integrand level and then fix the coefficients. So this was carried up to 10 loops, and so there is a big wealth of data for that. And as I mentioned, there is a relation with the amplitude. So you not only have the 10 loop correlator, but you also have the 10 loop amplitude. Now, much less is known for the integrand.
Sorry, in the slide before, you had some points in different colors on the graphs. The marked.
They just, I think it's just about the valency of the points. So red is 5 balance, and yeah, just to distinguish.
Oh,
so
okay, yeah, thanks.
Yeah, well, one feature of the graphs I didn't mention is that, well, of course, they are not labeled because remember you have this full permutation symmetry. So when you start spelling all these permutations, is basically about the different ways you have to choose the labeling of these points. So what are the 4 external points and what are the Lagrangian insertions? That will give you different tests on these permutations. Yeah, so that was about Uniprime, which has been very well studied because of the motivation that it gives you for free the amplitude. But then much less is known about higher weights, operators with higher scaling dimension, because they are seemingly more complicated. The fact that they have larger R charge tells you that in general, they are given by a sum of R-charged structures. So here you have exponents of this propagator Dij. So Dij, it's just Yij squared over Xij squared. And this is traced by some function that is just a function of Xij squared. So for the case of 20 prime, there is no R-charge dependence because all the R-charge was taken care by the SUSY prefactor that I showed at the beginning. But now the only thing this SUSY prefactor does for the case of higher R-charge is just it decreases by 2 the degree. But then there are still many possibilities. So now you have to bootstrap many of these functions, and they are still simple rational functions. So they still have simple poles, which again come from analysis of OPE. But they are less symmetric, so you don't have this full permutation invariance. So there are less constraints. But fortunately, it was possible to show some recursion relations that just tells you that if you shift by one of these breaches, so here, well, I should explain this part better maybe. There are 6 of these indices, which are just exponents of these propagators. And this is the list of numbers that I have here. So in this equation, what I'm saying is that I can shift by one of these entries, and people showed that the unshifted and shifted one, they are both related. This equation basically tells you that they have the same singular part. they have, yeah, so the part that contains this pole x12 square is identical. So this is something that people showed that it holds up at least up to 3 loops, and they also had to use planarity for that, and some the key feature was some universality of OPE structure constants. Yes, and so this helped fixing results up to 3 loops, and then there was another group that wanted to push things to higher loops, and they actually had to do some much harder work, because they also had to evaluate the conformal integrals and compare with data from integrability. But at the end, they managed to push this program up to 5 loops. So this is the data that is available. And thanks to all this data, and by spending some time analyzing them, it was possible for us to repackage all of these integrands. So before I introduce this repackaging, let me do some warm up on what I'm going to call the generating function. And this warm up, I'll just do it for the free theory. Yeah, so if you do the free theory correlator, you just, for these scalar operators, you just do big contractions with this propagator y over x. And in general, the answer will be given by some sum of these structures, where all this product just labels one graph, one possible big contraction, where you have this possibly 6 connections between the 4 operators, and these exponents are just the number of propagators flowing on each edge. And these coefficients, they will just come from the combinatorics of the number of ways you have to draw this graph. So what I'm going to be defining as the generating function is simply the sum. So the question is, can I resum all of this in a compact expression that gives me all of the correlator at once? And yes, we managed to resum these big contractions, and the result splits into two pieces. So let me describe the first piece. One second. Okay. So the first piece has a very nice representation, and in order to spell it, I need to introduce a 10D distance. So I promote the 4D distance to 10D by just adding the scalar product of the R charge vectors. And in the same way, this transformation at the top implies this transformation for the propagator Dij. It just transforms like this, d over 1 minus d. So here, the way I present the first piece of the generating function is in terms of this 10D distance. And it's given in this way. So there are many terms here. In the second line, these exchanges just refer to exchanging the points of the preceding term. And I can tell you how it works. So the idea is that if you want to recover all correlators, you have to expand this in a series. So this just gives you some geometric series, and it will give you just a simple sum of 1 plus Dij plus the square and so on. And then by collecting the powers of Dij, you can recognize which correlator you have. So for instance, this first term here with the 1, it will generate all the graphs with arbitrary propagators on each edge, and but just for this frame, just a frame of a square. And if you add this extra D13 or D13 square, then you will have one of the diagonals. And then the rest of the terms are just permutations of these two. And finally, this one here, it gives you all the graphs that have the 6 connections. Yes. So nicely, this admits some 10D representation. Unfortunately, then the extra piece that I am not giving explicitly here, it doesn't admit this representation. But that's perhaps okay because so the type of graphs that is generated by this extra piece are graphs that are somewhat special. They are these graphs that have some kind of extremality where, well, the distinctive feature about these graphs are that it's always possible to remove one edge and then the graph becomes completely disconnected. And these graphs actually do not appear at higher loops. Like when you compute corrections, these R-charge structures do not appear. So you can say they are protected. So this gives some, maybe some hint that perhaps a nice 10D representation of the integrand also exists. So let me continue with the warm up by doing now one loop. So yes, at one loop, the integrand is actually very simple. The fact that you have simple poles and the degree of the numerator of these F structures is fixed by conformal symmetry, completely fixes all the integrand. So one loop, you can actually fix all the integrands, and they all the R-charge structures happen to be all the same and equal to the case of 20 prime. And because they are all the same, they can be taken out of this sum over R charges. And then what you're left with is just a constrained sum of these R charge propagators. So then again, we asked the question if we can resum this. So nicely, when you resum over all possible weights, this sum becomes unconstrained, and then you can see that well, you can check that you can repackage everything in just this simple propagate in this simple denominator where you shift x by y. So in general, so what you can rewrite this as simply saying that the full resum, all the integrands resum are given by the 20 prime integrand with this shift from 4D to 10D distance, with the special feature that you should take the R charge of the internal points to be 0. So you really recover the integrand. So now I am giving you some evidence of some 10D structure. Perhaps it's not a lot of evidence, but then we can still take the courage to conjecture that this holds at all loops.
Sorry, so just a technical question. In the previous slide, was it YI or YI5? Sorry, if you change in 14.
Yeah, well, but it's a scalar product, right? So you just need the y.
Okay, it's an old factor.
1ij square is yi dot yj. So you just need one of them to be 0 for the full, for the scalar product to be 0. So I just need to give 0 R charge for all the.
But then it really is looking like what Collier is saying, no? That this internal point, you can lose a Klein reduced from 10 dimensions, but then you only integrate over 4 dimensions, right?
Yeah, that's what I'm doing. And perhaps there will be situations where you want to turn on the y's of the internal points as well. Yeah, but not here. So here, that's what I'm doing. I'm turning off the R charge of the internal points. Yeah, so just let me spell the conjecture. So it's just this. So you take the 20 prime integrand, which is known up to 10 loops, and then you promote the 4D to 10D distance. And the way you go about picking a specific integrands is by, well, you can do this trick. So the basic thing is you want to expand for a small yij square. But if you put these betas, then it allows you to collect on betas. And then for all the collection that has these exponents, ki minus 2, it will allow you to just pick so the coefficient will be the integrand that has these specific weights. So as an example, I show you here, this is just the previous 20 prime integrand that I showed, but now I changed the 4D by a 10D distance. Yes. but if I have to, so this kind of make a 10D symmetry manifest, but then more strictly, in more detail, since I'm taking the integration points to have this 0R charge, so the previous expression becomes this expression here, where the basic algorithm is to just, so you take the 20 prime integrand, and then you recognize where where these distances are. So there are 6 distances between the external points, and for each of them, you dress it by this blue factor, which is just basically, so for x1 to a square, you put 1 minus t to 1, 2. And here you have all the poles, but then you only get the 6 poles of 1 minus dij, where dij are the 6 distances between the 4 external points. Well, just to give an example of how you go from that to the R charge structures is, as I described for the free theory generating function. Again, here you just take these poles and you expand them, like in this geometric series. You collect on the exponents of dij, and that will give you these R charge structures. So here I'm showing some of them. So you can recognize that they start becoming simpler as you raise the exponent of dij, these entries here in this list, until you reach the case when all the entries are sufficiently large, then you just get 0. And this is a common feature for all the higher loop integrands. And it basically comes from the fact that these terms in the numerator, all of them at least contain one of these blue factors that will always be canceling at least one of the poles. So in that sense, unlike the, remember the one loop case, all the R charge structures were the same. And that was because the one loop is special. It contains all the 6 poles. And because you have all the 6 poles, when you do the geometric series, you can generate arbitrarily large exponents of all dij. But that's not the case for higher loops. For higher loops, since you are always missing at least one pole, there will be this saturation phenomena. When all the breaches are arbitrarily high, then you will get 0. And that's consistent with planarity, because you actually expect that if you have so remember these exponents here, they are related to the number of propagators between the operators. And if you have a graph like this, where all the breaches are very large, so each of these edges have many propagators, and if you try to draw some loop correction and imposing planarity, these loop corrections will always have to cross these lines. They will have to interact with these lines. So if you have there some a number of propagators, you will always have some lambda to the a. So for a fixed order, like here 2 loops, if you have all these breaches to be arbitrarily high, then they will not contribute to 2 loops, as it happens here, that you just get 0 for this R charge. So this is common for all the higher loops as well. Yeah. But well, this is just the rational function that sits as the integrand. Then you may wanna have an expression for the full correlator, right? So in that case, you just need to dress the integrand with the integration, and then put back this prefactor. So what this will allow you now is to write the generating function for all correlators, not just the reduced integrand, but now all correlators. And you can write everything in terms of conformal integrals. So here, the conformal integrals are just 2 of them. So one of them is a genuine 2-loop integral. It's known as the 2-loop ladder. And it's just has this representation when each of these vertices are the points 1, 2, 3, 4. And these internal points are the ones you integrate over. And then there is a 1-loop square. So this is just the cross diagram or 1-loop ladder. So all the 2-loop correlators are given in terms of this basis of 2 conformal integrals, but the coefficients differ depending on the charge. And here, everything is repackaged. So these coefficients, I'm just showing 2 of them, and the others can be obtained by permutations, have this form. As you can see, well, they always at least cancel one of the poles. And if you want the all correlators, you do the geometric series. Similarly, you can do this for 3 loops. 1 second. So yeah, things look more complicated here, and perhaps.
So, could I ask a question? Sorry.
Yes.
So you said, I think you were saying that it was important to have planarity. Is it correct?
Yes. Yes, I'm correcting the planar limit.
Okay, so I'm just thinking about this 10 relation to 10D. You might expect if it was as simple as maybe relate to 10D Yang-Mills, it would also work for the non-planar sector.
Right. Yes.
So did you check explicitly that you can't generate integrands for the non-planar integrands from, let's say, the 2222 correlator?
I think there is immediately one subtlety, which is that non-planar corrections, you have one loop non-planar corrections for high weights, right? But for the 20 prime, you have to go to 4 loops to have the first non-planar correction. But still, I mean, that's kind of saying, expecting that maybe the seat, because here there is not only a 10D symmetry, right? I'm also saying that the seat of all correlators is the 20 prime. Perhaps at non-planar level, you have to come up with a different seat, but I haven't even tried. I don't know much about the data for non-planar.
Okay, thanks.
Thank you. Yes, so I just wanted to show the 3 loop, maybe for the people that are familiar with it, because this looks complicated. But so first, at the top, you have this product of 1 and 2 loop integrals. And then below, you have the genuine 3 loop integral. So for the people that know, this is just the 3 loop ladder. This is the tennis court. These 2 are integrals with disk topology. They also appear for the amplitude. And these other 2, the easy and hard integrals, are they don't have this topology. They really need the full sphere to draw them, and they are more complicated than the others. But all of them are known, thanks to the work by Drummond and collaborators. But here what I'm showing you are the coefficients that generate all the
Are they all combinations of this harmonic, whatever, polylogarithms, HPLs with 2 variables?
Yeah, I think it's a single value harmonic polylogarithm.
Single value harmonic polylogarithm.
Yes, I think so. Yeah. Yes.
There are no like elliptic type of things. Right?
Not the 3 loops. No. Yeah. And so, well, this is, we have, for this case, up to 3 loops, we have that the privilege of knowing all these integrals. So all you need after that are just the coefficients. And here are repackaged all the coefficients. So I am putting all the poles in this factor. And again, as you can see, these numerators always at least cancel one of the poles. Yes, so this is much more compact than the tables that people use the first time they found all these coefficients. So now this 10D symmetry allows you to repackage everything in a compact expression that you just need to expand in Mathematica. The same can be done for higher loops, but now what I can give you is a list of conformal integrals with coefficients of this type. But then if you want to perform arbitrary kinematical limits, you can't, because you don't know the integrals. Or maybe you can study the integrals in a specific limit, like it has been performed for like Euclidean OPEs to extract certain OP coefficients or anomalous dimensions of Konishi and other operators. But currently you cannot do better than that. But in principle, well, we give you a full prediction, and you will still need to do the hard job of computing the integrals.
Correct. So at each loop level, you have some basis of integrals. So of course, if you only know 20 primes, then you can just reconstruct the whole answer, right? If it's already integrated.
Yeah, integrals that appear in 20 prime. If you know all the individual integrals that appear in the 20 prime expression, then you have everything you need.
But then how quickly number of these terms you need to know separately grows with loop order?
It grows a lot. So here you have just 3 because tennis score is equal to ladder 3 to the 3 loop ladder. So there are only 3 genuine 3 loop. But then I think at higher loops at 4 loop maybe you have already 32 conformal integrals, and it just grows much more at higher loops. So yeah, it's still a hard job to find everything, but at least you have the coefficients now. But yeah, so that's the prediction. From 20 prime, you can obtain everything. But let me tell you that actually you have to be careful because there is a caveat about the prediction I am describing. Basically, what I'm telling you is that you take a seed, which is originally a 4D object, and then you promote it to be a 10D object. But this prescription suffers from some problem, which is that it could be missing some terms of the original 10D master generating function that vanishes in 4D. And that can happen because, as you know, well, if you have 5 vectors, they can be linearly independent in 10D, but they become linearly dependent in 4D. So because of that phenomenon, then you can have these vanishing terms that are invisible in this 4D object that we take as a seed. But that problem has been studied, and so what you need to find are these gram determinants. But we need to solve this problem of possibly vanishing terms is to classify all possible gram determinants that are consistent with conformal symmetry and also planarity. And we haven't done that full classification, but at least we have checked that there are not conformal gram determinants up to 7 loops. So we have a prediction that you can trust at least up to 7 loops. And at 8 loops, you will have to figure out if there is some gram determinant consistent with planarity that spoils the nice map between for this seed and the 10D generating function. Yes, so this would be the end of the first part of the talk. Now I want to use these results for an application. So let me.
Should you break now?
Yeah. So well, it depends. Yeah, we can take a break now. This is half of the talk. So the next part is equally large. Yeah, we can take the break now if you want.
Yeah, okay, sounds good. Then let's break for 10 minutes now, and people are welcome to have an informal discussion during the break.
This second part of the talk, I want to describe some application and exercise. So let me establish the goal of this exercise. As I was telling you before, one frustrating thing about higher loops is that you don't know the conformal integrals. It's just hard to integrate. But in this exercise, I will be focusing on a family of correlators which have been computed using integrability. So there are full analytic results for those correlators in terms of ladder integrals. So now that I have the integrand of all correlators, one thing I can do is to try to work out a map between the integrands and the analytic results. So ideally, the hope would be that you will be able to identify individual conformal integrals with a bunch of known functions. Yeah, so at the end, I will show that that's possible, but well, not in full generality. For some specific cases, it is possible. So yeah, let me describe what are these simple 4-point functions. One representation is the one in this figure. In the free theory, the idea is that you pick the R charge in such a way that there is only one possible big contraction, and you have frame the number of propagators on the frame, on the square frame, to be very large. So yeah, one way, this is the way to do it with R charge, but if you have a very efficient way, you just take the external unpolarized correlators, unpolarized operators, and you take this structure. So the coefficient of this R charge structure is what we call the simple correlators. And why are they simple? So basically the key for the simplicity is on taking this very large K limit. This is something I somewhat described before. Basically, if you want to draw loop corrections like this, some loop correction that connects the inside of this frame 1, 2, 3, 4 with the outside, then this will be suppressed again, just like what I described before. And because I'm taking K very large, all these diagrams are suppressed. So the net result is that you have a factorization between this frame inside and the frame outside. They don't talk to each other, and you can compute both if you are capable of resumming all Feynman diagrams with this topology. So if you are able to perform the resumation, then you will have your object that we call octagon. Well, you can call it a square, but we call it octagon because we also count these edges here. Yes. So this is the key feature. It has a factorization, and so you can say the building block for these simple correlators are just these octagons. And they haven't been computed using Feynman diagrams and resumming, but fortunately there is another way, which is using hexagonalization. Basically, you can compute an octagon by gluing two of the hexagons introduced by Pedro and collaborators. Yes, so if you use this building block, we can write a generating function for all these simple correlators. That's the sum of all correlators for arbitrary A and B, where A and B are the number of propagators in these diagonals, which are taken just to be any numbers. They are not large. They can be 0 as well. So let me show you here the way you compute the generating function. So this first expression is seemingly complicated. I am using some Kronecker deltas, and the effect of Kronecker deltas is just to say that each term, they are, so when one of them is 1, all the others are zeros. So that's the feature. That's why I use these Kronecker deltas, just to make them all mutually exclusive. And they represent just the free theory big contractions. So this first part stands for just the case where you have this frame. This second part here stands for the case where you have diagonals, arbitrary number of propagators in the diagonals, but you have both at the same time. Both are non-zero. And that's why you have this factor of 2 here, because you can swap them, which one goes inside, which one goes outside. And then these other 2 cases just describe the case where you have only one of the diagonals with arbitrary number of propagators. And because there is no, the other is not present, then you can split them. You can still draw a planar diagram where you split this number of propagators. And so you have a sum of over the ways of splitting. So that's what this sum here stands for. But that's the free theory. When you want to promote it to the full correlator at finite coupling, let's say, then you just dress it with these building blocks. So you have, because I described that they don't talk to each other, you have an octagon that is labeled by the bridge that is in the diagonal of this square. And this seemingly complicated expression actually nicely, it turns out you can show it's a perfect square. So maybe it's not obvious, but if you expand this, you will get exactly this expression here above. So there is a nice representation for it in terms of a building block that we know even at finite coupling, thanks to the study of integrability. So now you can ask if I can obtain the same type of result from the integrand. Like that's the integrand of the generating function of all simple correlators also is it also a perfect square? So the answer is yes, and let me show you why that's the case. So first of all, if you are going to get the integrand, one way to do it is the old-fashioned way. That means you tell me which are the R-charge structures, these Fs, that contribute to the integrand. And because I'm taking this large R-charge limit, then 4 of the entries are infinity, or just arbitrarily charged. Sorry, arbitrarily large. They have to be larger than the loop order. And yes, so that's the way to do it with these R charges. But actually, our message is that you should forget about these R charge structures. Now we are giving you a generating function that has everything. So you can find a better way to extract the correlators you want. And for the case of the simplest correlators, because you have this limit of large R charge, you have to recognize that the only terms that will contribute to this R charge structure are the terms that contain the corresponding poles. Why? Because as I showed you before, the way you obtain all the R charge structures is by expanding the pole in a geometric series, right? So if you want to reach arbitrarily high exponents of these propagators, then you must have the pole. If you don't have the pole, it will truncate at some finite exponent. So, for this reason, one way to obtain the generating function of all simplest correlators is just by identifying all the terms with the poles. And one way to do it is just by taking this limit, where you take all all these propagators of consecutive points to go to 1, and you can also recognize that that's the same as taking a 10D null square limit. So you are just taking x going to y. And so this is our prescription. If you want the sum of all simplest correlators, yes, all the simplest correlators, then you take this generating function of all correlators, you address it with this factor. So what this is doing is removing the poles from the terms that have the poles and giving zeros to the terms that didn't have the poles. So now when taking the limit, all those terms without the poles vanish. And so this is giving you the integrand for all simplest correlators. Now, what is it? And does it square or not? Yes, it is square. So here there is a prefactor that is something that is just the free theory. This is the free theory resumation. That's something that you can instance check with the previous generating function of the free correlators that I showed you by taking the 10D limit. And then it's addressed by this factor. So, but why is this factor a square? Actually, it has a simple reason, and it pertains the null limit of the 4D correlator. So remember, my prescription is that you take a 10D null limit, but actually you can check that these two operations commute. The operation of taking 20 prime and getting the generating function by extending 4D to 10D and then taking 10D null limit commutes with first taking the 4D null limit and then promoting the distances to be 10D distances. Yes, so the simple reason is that remember that if you have the pole in one case, then that will give you a pole of 1 minus d. So if you have the pole xij squared in this expression, you will get a pole 1 minus dij for the generating function. So it's just the terms with poles, with the poles that you want, completely match. But remember that this relation gives you the amplitude integrand. So then the message is that this factor here can be obtained from the amplitude integrand by making a simple replacement. Well, in general, it would be the 4D distance to 10D distance for all the 6 pairs, but because I'm taking the other 4 pairs to go to 0, actually the amplitude integrand does not depend on the other 4 pairs of distances. So you only need to do this taking x13 squared to 10D and x14 squared to 10D. Yes, so now we have 2 expressions for the same object, both of them square, and we can just compare. So in the comparison, I take the root square, and so this is the expression obtained from recognizing that there is a building block that is the octagon, and this is the expression obtained from the 10D null limit of the integrand, which relates the generating function to the amplitude. Immediately, one thing you can notice is that if you take D13 and D24 to 0, this sum collapses to just the first term, to the octagon with bridge 0, and this prefactor disappears, and this generating function becomes just the amplitude integrand. So the first immediate consequence of this equality is that the octagon with bridge 0 has exactly the same integrand as the four particle amplitude, with the sole difference that when you are going to evaluate the integrals, now you should take them off shell, as opposed to the on-shell evaluation of the divergent for gluon amplitude. Of course, this is a nice result that deserves further study and also further comments. And I will comment a little bit about this at the end. But for now, let me stick to the original goal, which was to try to match conformal integrals with the specific with the analytic functions that are already known. So the analytic functions that are already known.
Right, Frank, I'm confused. Very beautiful result, but I'm confused because the octagon is finite and the amplitude is divergent. So how could they have the same integrand?
Yeah, it's on the evaluation of the integrand. So it is the same integrand, but the prescription is that the four gluon amplitude is evaluated on shell, and the octagon is evaluated off shell. So on this different prescription of how you integrate comes the difference that one is divergent and the other is finite. So that's a key point. But remember, so here you're taking the 4D distance to go to 0, which for the amplitude means that the mass is going to 0. So the mass of the particles are 0. And here you're taking a 10D distance to be 0. That, if you translate to 4D objects, that's xij squared equal yij squared. So the 4D distance is not being taken to 0. It's just something finite. So that's the off-shellness. That's the off-shellness of the octagon.
So would then this octagon provide an amplitude in the Coulomb branch, or some kind of regularization of the amplitude, which is not dimensional regularization, but?
I have comments about that in my last slide. Yes, maybe we can discuss that. I mean,
I see.
Yes, that's exactly my last slide is called Coulomb branch. Yeah. So, but as I said, let me stick to the original goal, which is. I mean, we found a nicer result than the original motivation, but let me try to finish the story of the original motivation, which was to work out a map between conformal integrals and analytic functions. So in order to do that, what you need to do is to just collect the coefficients of D13 and D24 on the left-hand side and compare them with the coefficients of D13, D24 on the right-hand side. But for that, I have to make explicit what are these coefficients on each of these objects, octagon and the generating function. The octagon is known from integrability, and it takes this form. So it has a sum over this integer where you have this exponent, and this is the explicit dependence of octagon in D13 and D24. And then there is another function which has this structure. So it has a label n, and for the label n, it starts at order n squared in the loop order. And is independent of D13, D24, and is given is completely known as a sum of products of well-known ladder integrals. These ladder integrals are single value harmonic polylogarithms, and they are well known. They are explicit results for them. And the generic result from integrability is that these functions here are completely known as this sum. So for the object with label n, you have a product of n of these ladder integrals. So that's known. Sometimes this can even, well, not sometimes, this can be refined to be a sum of determinant of ladder integrals. So that's something I will show at the end as well. Yes. So you just plug in this expression back on the top, and then you also work out what's the D13, D24 dependence of the amplitude. So this is what I described in the previous slide. And this part, this is the amplitude. So what is this function AKMN? So K stands for just the K loop contribution to the amplitude integrand. And M and N are just the exponents of x13 and x24 that appear in the numerator of the integrand of the amplitude. So the amplitude integrand can be organized into groups, where each group is labeled by these two numbers that are just exponents of these two factors in the numerator. So that's everything you need, because then my prescription tells you that you shift this 4D to 10D, and that has the effect of dressing this group with 1 minus D13 to the m and 1 minus D24 to the n. And this is everything you need to compare. So now you do some simple algebra and you compare. The idea is to work out this, to find a map between this contribution I and this contribution A. So A are a bunch of integrands that whose integral are mainly not known. And these guys here are completely known, as I described here, that is given by non-ladder integrals. In general, the map turns out that doesn't work one-to-one, because unfortunately these guys proliferate much more than the ones in the left-hand side. But still, for specific cases, you can work out a one-to-one map, and that's what I want to show here. First term for which things work one-to-one is this specific case. So is for any n and l, and in the amplitude side, the two indices take these specific values, n and n plus l, at leading order. So the leading, remember this, the way I define is that these guys start at this order. So the leading order contribution of this function psi equals the group at this loop order with these indices n plus l and n. So the right-hand side is known and is just a determinant of ladder integrals with this shape. So specifically, the diagonal is just all the odd numbers, 1, 3, up to 10 to n minus 1, and they are shifted by the bridge L. And then the way you get all the other terms is just by shifting by 1 when you go down, and by, yeah, you shift by 1 up and down. And in the left-hand side, this is the fishnet. So this is something I haven't proved, but it's probably something you can prove, that if you say that you want the amplitude integrand, all the terms that have at this loop order, n times n plus l, with these exponents of x13 and x24, at least the data up to 10 loops, which are provided by Heslop and Burgelli, show you that that all you have in this group of integrands is just the fishnet. So it has a single element. And as I said, that's probably something that can be proven. So this reproduces a result that was conjectured by Basso and Dixon and later proven by Olivucci and Derkachov. But here it's coming nicely from our generating function and taking this tending a limit and comparing our octagon expression with the integrand. So we get this for free, and it's consistent with Basso-Dixon conjecture. Now there is yeah, so there is an extension of this. This was the leading order for these terms, and actually nicely you can also work a map one-to-one for the next subleading order. So you just shift by 1 the loop order. Again, this part from integrability is known as a determinant. Is the same determinant as before, except for the indices of the last column are shifted by 1. So the transcendentality grows as it should for Hyperloop. And but this part here is more complicated. So this part.
Sorry, I just lost a bit. So could you repeat? Probably already answered to Pedro. So the right-hand side is a function of the cross ratios, right?
Yes.
And when you say integrand, it should be a function of billion of x's.
Yes. So here, yeah, maybe I'm abusing a bit of notation because I'm changing from integrand to integrated expression. But yeah, what you should take here on the left-hand side is the integrand integrated. Yes. So the labels. So it doesn't make
but
sense.
not in the right kinematics, kind of, right?
Could you say again?
Not in the light-like limit.
No. I'm evaluating off shell. Yeah, that was the the comment here that
when you actually need it is when z goes to what, 1 or 0 or something like that? For the amplitude purposes, when at which values of z you need it?
Z being the cross ratio.
Yeah.
Well, you mean when you want to go from correlator to amplitude, you take the null limit. So you take z going to 0 and c bar going to 1 or infinity. But here, yeah, maybe I should explain this better. First, I am relating these octagons to the integrand of the amplitude integrated off shell. So you should integrate it off shell. And as I said, the reason you integrate off shell is because I'm taking a 10D null limit, which means that xij is equal to yij. So xij is finite. It's not be taken to 0. It's not making contact with the massless 4-particle amplitude. Instead, it's giving some off-shellness to the external momenta. Yeah. So technically speaking, you take the integrand and you evaluate off-shell. So that's the map I am working. I'm comparing two finite quantities. So the function from the octagon that are known against an integral that evaluated off-shell gives finite results.
I think maybe I don't know if that's related to what Collie is asking, but what some people could be confused is that if you have the amplitude and then you take this no limit, then it should somehow diverge but become the usual amplitude, right? But the usual amplitude is gamma cusp, and the gamma cusp is not in all this ladder business, right? It's more it's
yeah.
So where do we see gamma cusp, for example, in this game?
In the amplitude. But so I make a comment about it at the end. Let me finish with the map. I'm just a step away. But for these maps, it's you take everything off shell, and yeah, just let me for the people that are interested. So the way you describe this integrand integrated off shell is given by now is not given by a single term like it was for this case where it was just one fishnet, but now it's given by a family of three types of graphs. And in order to describe these 3 types of graphs, I will first give you an example. So the first of these examples appears as 5 loops where n is equal to 2 and l is equal to 0. And you have just this identity. Notice that it's just well, you can describe it as the fishnet, the form. So this is a fishnet where you're putting a diamond in the middle point, like a 2x2 fishnet. And here you're putting a diamond that is much larger. And here, here I forgot to correct that there is an extra line. So you have 5 faces, right? As you should for 5 loops. So here is, again, the 2x2 lattice, but then you are, one of the boxes, you are making it into 2 boxes. So it's easy to describe how you deform the 2x2 lattice. And at 5 loops, this combination with this important negative sign here gives you a determinant of ladders. And yeah.
So sorry, just to understand still. So you have this octagon which computes certain type of diagrams, right? Then you use this duality with amplitudes, and this maps you to some different type of diagrams. Is it
right?
And then these diagrams, aren't they just kind of dualized diagrams? Can you just like do this identification without just at the level of the diagrams from the beginning?
Yeah, exactly. Yes. So indeed, the diagrams of what I'm showing you here is the momentum representation, right? I should stress that as I said, the relation between momentum and x is just that you identify this consecutive distance between I and I+1 with the momentum pi, right?
So you know some subset of diagrams from integrability, octagon, whatever, and
yes.
and now you're just dualizing those diagrams and telling us some combination of those related to the known answer. That's
what I'm doing, and stressing the fact that these diagrams are evaluating off shell. So the claim is that off shell, I obtain this final result that I know thanks to integrability.
But then in terms of this previous story about 10D and no independence on the surcharge factors, how is it related? Because it seems like you just work with diagrams, conformal diagrams, map.
No, but it's not true, Kalia. It's not true. You don't work with diagrams. The octagon is not, no one knew before what Frank is presenting today, the various terms of the octagon, how to relate them to Feynman diagrams. It's not true. The octagon is one correlator. It's all Feynman diagrams. It's all a mixture. It's a mess. What Frank is showing is how to disentangle this mess into beautiful stuff.
But that, like, perturbatively, you know what are the diagrams or not?
No, of course no.
They were known up to 5 loops because Vasco and collaborators work out the integrand. But now I am extending that, right? That was the first part of my talk. I'm getting all correlators. So for the first time, I am getting the integrand of the octagon up to at least 10 loops. I say 10 loops because 10 loops is the result for the from Burgelli and Heslop for the 20 prime correlator. Yeah. And what I'm showing you here, you can say that it's basically patterns. So I recognize in those results that there are patterns. So for the previous case, the pattern shows that this specific family only has the fishnet. And now for the next subleading order, you have this type of diagrams that can be described as the formation of the fishnet.
But at least up to 5 loops where you know identification with perturbation theory, what you describe is dualization of those diagrams. Is it correct?
Yes. So I am abusing the notation here because I am putting the notation that amplitude people use. But of course, the diagram that you evaluate is this dualized diagram that I was drawing here.
So basically, you take advantage that in one side, you know, up to 10 loops, right? And then try to import this diagram knowledge into another side. That's the summary?
Yes. So the integrand of the octagon was not known except up to 5 loops where there were results. Now, at least I know it up to 10 loops because my 10D symmetry result for all integrands allows me to take advantage of the 20 prime 10 loop result and extend it. So now I have the octagon up to 10 loops in terms of these diagrams. And when I evaluated off shell, they should match with the results from integrability that are known up to all loops.
All right, I'm still confused, but let's postpone for after.
Oh, okay. Yes, but yes. So yeah, I just want to finish here by saying that this is the example of 5 loops, and then if you want to have the generic result, all you do is you take these 3 types of deformations that I described for the 2x2 lattice, and you perform it for every 2x2 sublattice in this big fishnet. So you pick every 2x2 sublattice and you perform these 3 deformations. So you get many terms and you group them into 3 families. And these 3 families also come with this positive, negative, positive sign. And they evaluate off shell to this determinant of ladders. So that's why I call it beyond Basso-Dixon fishnets, because that's what it is. Yeah. And you can work higher maps, but in general, what you will obtain is that there is a linear combination on the right-hand side or a linear combination on the left-hand side. And it's harder to work a one-to-one map. But yeah, when I publish the paper, the data will be available. So maybe people can recognize more patterns than the ones I am presenting here. Yes.
So are these more general diagrams appearing in some other fishnet theory?
Whether these diagrams appears on the formations of the fishnet?
Yeah.
Yeah, I don't know. Maybe you guys should know better. Yes. No, I haven't explored how. Yeah, you can ask whether the first, right? Because the fishnet is a stream limit, right? You can ask whether the first correction 1 over, what do you call it? Is it?
Yeah, call it sub-fishnet diagrams, sub-fishnet diagrams, right?
Right, maybe the first sub-fishnet diagrams, right, the ones that enhance to the full gamma or beta deform n equal 4, maybe they appear, maybe these guys appear as the first corrections. So,
Okay.
yeah. Yes, that's
who studied these sub-fishnet diagrams and who introduced them? I did not know this name before.
I
What is
introduced just now.
Okay. Is there any paper with this with discussion of these sub-fishnet diagrams?
Well, I mean, in a sense, maybe Kosik got closest to describe something in the Slaughter's limit. Right?
Who?
Kostya.
Okay, thank you.
But yes, it would be nice to find whether these guys appears on the series around the fishnet. Maybe is the first subleading term. So just let me make a summary of what I've done. So in the first part of the talk, I showed you that you can take the 20 prime integrand and promote it from 4D to a 10D distance. And that gives you a generating function of all integrands and correlators. And then I explored the case of a family of simple correlators, and I show you that they can be obtained from a 10D null limit. And the highlight, one of the highlights of that is that the simplest of all these simple integrals, which is known as octagon square, is identical to it has the same integrand as the amplitude, but there are two different prescriptions when you evaluate. One should be taken off shell and the other on shell, basically because this, in terms of 4D, is just saying that the little x is taken to be equal to y. So both are still finite. They are just taken to be the same, but they are still finite. So that's why here's off shell. And here is a genuine 4D null limit, so it's on shell. So let me finish by further making a comment about these two objects. I don't have an explanation for why they have the same integrand, but maybe one can say that you may need to go into the Coulomb branch to find an explanation for these two, for relating these two objects. So the left-hand side is the story about the four-gluon amplitude, and the right-hand side is this new story about the octagon, suggestively drawn as an amplitude as well. Here, the left-hand side is a story by Aldai, Plewka, Hen, and Schuster, where they came up with a way of regularizing the amplitude, an alternative to dimensional regularization, where they noticed that you can go into the Coulomb branch, you can give masses to some of the particles, and that's enough to regularize the divergences. So by giving a mass to the particle that runs in the perimeter of this diagram, that regularizes all divergences. The rest is still massless. So here the thick line represents massive and everything else is massless. And first you take that maybe finite, and then you take the limit where this mass goes to 0, and that gives you a regularized four-gluon amplitude. So as you guys were mentioning before, so as usually it's well known that the result for the four-gluon amplitude is just the one loop amplitude exponentiated. So that's these logs here, but then dressed with a coefficient that is known as gamma cas that controls this divergence and is known at finite coupling thanks to integrability. There is another story now, which is the same integrand, so that's why I have the same graph. But now the massive particles are the ones, are the external ones. So this could be like a particle amplitude of massive particles, and everything else here is just massless. Here, as I described, you take first things off shell. So these distances are still kept finite, but we have further studied the case where you take these distances to go to 0. And then it's known that the result also exponentiates. It's also given by a log square, like the foreglown amplitude. But now this coefficient is gamma octagon. So it's a different function of the coupling. One nice thing about this comparison is that, these two coefficients have been recently they have been identified as belong as part of a family of functions. So there is Basso, Dixon, Papatanat, they show that there is an interpolation between these two quantities. So there is some parameter on an integral equation that when you solve the equation for a parameter taking value 0, you get gamma octagon. If it takes value pi over 4, you get gamma cusp. So there is an interpolation between these two quantities. And then you can ask whether there is an interpolation between these two guys. And we would like to say that possibly this lies on the Coulomb branch. So there should be some amplitude in the Coulomb branch that has external masses and also internal mass. And then depending on which order of limits you take, which masses you take to 0 first, you will either land on the foreglown amplitude regularized, or you land into this massive four particle amplitude. So yeah, this is some of the question and the speculation that the Coulomb branch may explain the interpolation between these two quantities. Yes, so that's what I had to say about the Coulomb branch. And yeah, just let me finish with some kind of outlook. Of course, I haven't explained the origin of this 10D symmetry, so it'd be nice to explore the origin of it, whether it's at all related in any way to the same 10D symmetry in the Sugra limit, or maybe not. I have only explored the 4-point correlator, but I think possibly you can find maybe this same 10D symmetry for higher point correlators. Unfortunately, there is not much data for them, so that's why it hasn't been performed. Well, one can speculate on a possible relation between the simplest higher point correlators, right? Like, for instance, the decagon recently studied by Tiago and Vasco, that may be also some 5-point massive amplitude. And well, as I mentioned at the end, it would be nice to explore this interpolation in the Coulomb branch, taking into account that there's also already a story between gamma cusp and gamma octagon. Yeah, and maybe this exploration will also generalize these maps between conformal integrals and analytic results obtained from integrability. Yeah, so that would be the end of my talk.
Thank you very much, Frank, for the very nice talk. So please thank Frank. Please unmute yourself if you can.
May I ask Frank?
Please, Bologna.
Hi. Could you show again these, how do you call them now, sub-fishnet diagrams? Yes, these ones. Will they appear, suppose you expand n equals 4 Young-Mills around the fishnet limit. Will they appear, will these diagrams precisely appear if you expand? Are they related in this way to n equals 4?
Well, they are certainly on n equal 4, but whether they will appear as the first subleading correction to the fishnet, that's something that we don't know.
Yeah, that could be, I mean, this could be maybe combined to integrability. Maybe these graphs would combine in your combination of these ladder function, this f1, f4 minus f2, f3. At least it's a very appealing hypothesis. Integrability could be related to this kind of factorization.
You mean this separation of variables method? Or?
Yeah, suppose those diagrams appear in the next order, in the next to leading order of fishnet, and precisely in this combination, and they factorize in the way as you show in the right-hand side.
Right.
Would be quite exciting. I mean,
Yeah.
it's not a question, it's a wishful thinking.
Yeah, we don't have also an explanation for this combination. I mean, here I explain in a technical way why they appear that way. As I said in my exercise, I'm just comparing exponents of D13 and D24, and that has a consequence, this specific combination. But we don't know in general what's the principle that groups these diagrams to then give you determinant of ladders. In general, I mean, from this exercise, we have a much larger family of relations. Like the left-hand side will be a bunch of sum of diagrams of this type equal a sum of determinants. So here I am showing you just the nicest examples where there is a single determinant on the right-hand side. But from the exercise I have described, you can also obtain more complicated relations, but always determinants of ladders. So yeah.
Well, your result is that you always can, how to say, combine these diagrams in linear combinations with specific coefficients such that they render this kind of determinants.
Exactly, yes,
Mm-hmm.
yes.
It's not an observation about n equals 4 super young meals, it's just an observation about diagrams so far.
Yeah.
Mm-hmm.
Yes.
Okay.
Yes.
Maybe that's where the integrability can show up.
Right, we don't have a proof of this, but it's a consequence of this 10D symmetry.
Mm-hmm. Mm-hmm. Oh, very nice.
There other questions?
So would you conjecture that the octagon is also a scattering amplitude? Is the octagon equal to a scattering amplitude or not?
Yes.
So the
Yes,
octagon, if I replace distances by momentum square, it is a new result for a scattering amplitude in n equals 4 at any value of the coupling.
Yes. Yeah, perhaps there is more to say about that. When people study the integrand of the amplitude, as I briefly mentioned before, they usually study the higher D integrand because they usually want to take the they want to take the dimensional regularization, so they need higher D. So it has been understood that it's possible to construct the 10D integrand and then use it for your purposes of whether you want to use dimensional regularization or you want to use the Coulomb branch regularization, where you take the extra 6 dimensions to be the masses of the particles. So this is basically what one of the interpretations that I am taking these extra 6 dimensions to be the masses.
I'm just trying. So how would you realize this amplitude in terms of the original D-brane construction? So the left-hand side, you separate some D-branes and you consider open strings that end on the separated D-branes, right? And then when they connect to the large stack of D-branes, they form this thick line, right? And then inside the thick line, you have the usual gluons that run in n equals 4, right? In the stack of D-branes.
Mm-hmm. Yeah.
Do you have a similar picture for the right? In the right, what is it? You scatter W bosons instead of photons? You separate the stack again, but do you scatter something that joins one index of the big stack with one index of the small stack?
Yeah, well, the separation of the stack of branes, I guess, would be just the same. But what is going on different is what's going on S5, right? What are the specific bets you are giving? So the story of Aldai and Hen and collaborators, you just give a bet to one of the scalars, I believe. So here on the right-hand side, you have to have a more complicated configuration of bets in such a way that you can you give different masses. The story of this regularization on the left-hand side, actually, the full story contains masses for all the external and also the internal. But unfortunately, they depend from each other. So when one of them is taken to zero, sorry, when all these four masses are taken to be the same, then all the masses, all the external masses become zero. So there is some dependence. But that's because you are just picking one scalar to receive a BEP. If you want more freedom, which is what we need for the octagon, you give BEPs to more scalars, and then you can control the masses independently.
By the way, I forgot if we already discussed, but another possible object to consider here is locally BPS polygonal Wilson loop, because 10D null limit is basically locally BPS condition for the Wilson loop.
Right. Sorry, you mean
but it's slightly different from like scattering amplitudes of the W bosons that you're discussing here, because you need to take like a large mass limit in order to relate it to the 10D, sorry, the locally BPS polygonal Wilson loop.
Mm-hmm.
But if the, I think, relevant object is just the ratio of the masses, then there might be a possibility that this object can also describe the locally BPS polygonal Wilson loop, I think.
Mm-hmm. Is it sorry, you said null polygonal Wilson loop or
no, locally BPS. Null polygonal Wilson loop is a very particular case of locally BPS polygonal Wilson loop.
Mm-hmm.
So it's not null, but like how much it is now is canceled by like how you change the scalar coupling of the low BPS Wilson loop.
Mm-hmm.
Much like what's happening here.
Okay, I see. Yeah, I will look into that.
So those Wilson loops normally, aren't they the ones that Kostya considered? Those normally are trivial, but maybe here because we have cusp.
No, because we have cusp and then the scalar coupling changes along the Wilson loop. It's locally BPS, not the BPS Wilson loop.
So the string dual of those is not a wordsheet touching the boundary, but
well, it is a wordsheet touching the boundary. So it's different from Coulomb branch amplitude if you consider the ADS picture, because like in this picture, so you're discussing like a W boson amplitudes. For that, you need to have like a several probe branes, and then you consider an open string stretching between them, right? And then if you do the de-dualization, then you have some like a D instanton not touching the boundary, but somewhere in the bulk.
Mm-hmm.
But if you consider locally BPS Wilson loop, then you have some open string really ending on the boundary, but it's not the null polygonal Wilson loop.
So should I stop recording? I just had to take a call.
Yes, maybe. So let's thank Frank again, and then we can continue discussing.